In level 4, we'll be solving applications of exponential functions and logistic growth functions. Some of these problems will be using a calculator. Looking at this first example, it says to use a calculator, we're going to find the shortest distance from a curve of f of x equals e to the x to a point 3, 1. Now, this problem is going to show up over and over again in many different settings. It can be applied to an exponential graph. It can be applied to any other graph. It's really important for calculus. So, the way this works is it's asking if we have the curve f of x equals e to the x, which looks something like this. My y-intercept at 1. We're trying to find the shortest distance from this curve to a point 3, 1. So 1, 2, 3, up 1, about there. And if I draw a little segment to the graph to make it as short as possible, it might look something like that. And I'm trying to find that shortest distance. Now, I don't know what point on the graph is going to be the closest. So I'm trying to find some xy pair right here that's closest to the point 3, 1. And the way I'm going to do this is using the distance formula. So I'm going to set up a distance formula equation. And remember, the distance formula is a giant square root. We subtract the x's, x1 minus x2, square it, plus y1 minus y2 squared. And we want to write a formula for the distance between those 2 points. But we want our equation to only have one variable. So just like we did with those area problems, we want to write our y value in terms of x. Now this graph is y equals e to the x. So we can replace y in our xy pair with e to the x. So instead of xy, we're going to think of this as x comma e to the x. And that came right from the function right here, f of x equals e to the x. It's just like y equals e to the x. So now in my distance formula, I'm going to use these 2 points, x comma e to the x and 3 comma 1, and plug them into the distance formula. So I get the square root of x minus 3 for my x values, and then I square that, plus, and then for the y's, I replace y with e to the x, and then I subtract the other y value, which is 1, and then we square that. And this function represents the distance between the point 3, 1 and any point on the graph of e to the x. Now we're trying to find the shortest distance, so what we're going to do is plug this function into our graphing calculator. So go ahead and plug your giant distance formula function into your graphing calculator and y equals. If you graph this function in the standard window, you might get a graph that looks something like this. And remember that this function represents the distance. It represents the distance from the point 3, 1 to any point on the graph. And we're trying to find the shortest distance. So we want to find the minimum point of that graph. So do second trace, minimum, go to the left, go to the right, and find that minimum point. You should get the point 0.74 approximately and 2.51. Now, the first coordinate is your x, and that's the x coordinate of your point that's the closest. The shortest distance is going to be the second number. Shortest distance. So So the answer to part A, find the shortest distance from the curve to the point, the shortest distance is going to be about 2.51 units. Now in part B, find the point on the graph of f of x that's closest to the point 3,1. Now we're trying to find the coordinates of our xy pair, and we already have the x from our point. So the x coordinate is 0.74. To find the y coordinate, we're going to plug that x into our function e to the x. So y is going to be e to the 0.74, which is about 2.09, well, we'll call that 2.10. And so the point is 0.74, 2.1 approximately. That's your xy pair that's closest to the point 3,1 from that graph. This next example is an application of an exponential function. It says when a certain drug is administered to a patient, the number of milligrams remaining in the patient's bloodstream after t hours is modeled by the function d of t equals 50e to the negative 0.2t. Use a calculator to answer the questions. Okay, part A says how many milligrams of the drug remain in the patient's bloodstream after 3 hours. Well, first of all, in our exponential function, the number in the front is the initial value. And we're going to do this by graphing this in our calculator. So go ahead and plug in 50e to the negative 0.2t into y equals. And you're going to have to change your window. When you graph this, for your x min, this is time, so time can't be negative, we'll make it 0. X max, we're looking at the hours where a drug remains in a patient's bloodstream. It's probably not going to be more than 12 hours, 10 might be high enough. Something like that. You can play around with it. And then for y min, the function represents the number of milligrams of the drug, and 50 is going to be the initial value. So when time is 0, you would start off with 50. That's always the initial value of an exponential function. So, and then the negative exponent indicates that this is going to be an exponential decay function. It's going to be decreasing. So 50 is going to be the highest you ever have, which makes sense with the drug in your blood. It's going to decrease. So the highest we would need for y, well, the lowest for y min, it's never going to go below 0 because we can't have negative values. But for y max, we need to go up to at least 50. You could go up to 60 if you want to go a little higher, but since it's going down, we don't really need to go much higher. And then when you graph this function, it should look something like this. And the question is, how many milligrams of the drug remain in the patient's bloodstream after 3 hours? The easy way to do this is to skip all this graphing and just plug 3 in for t. So we could have just done 50e to the negative 0.2 times 3, and you get about 27.44 milligrams. The other way you can do this is you can trace the graph and plug in x equals 3, and it will give you the point 27.44. And you could also do second trace value, and that lets you plug in an x value, so you could plug in the x value of 3, and it would give you the corresponding y value. But for part A, where I'm just plugging in a value of t, I really didn't even need to graph it. But when we get to part B, we will need this graph. So part B is asking how long it will take for the level of the drug in the patient's bloodstream to reach 10 milligrams. This time I want to know when 50 e to the negative 0.2 t will equal 10. And I don't know how to solve this equation by hand yet, so I have to use the graphing calculator. So the way it's going to work is we use our little graph from the same graph we kind of used in part A, and we want to know when it equals 10. So what we're going to do is put in a y equals 10 line. So go to y2 on your graphing calculator and just plug in 10. And then you're going to find the intersection. So go ahead and do that. So we do second trace intersection, and you should get the point 8.047, comma 10. So that means it's going to take approximately 8 hours for the level of the drug to reach 10 milligrams in the patient's bloodstream.